So, okay, what I want to do first is get your data into Excel. Why do you think we ran 5 trials? Oh, good. To see if any one of them was fluky. If we take a look at each data set, then we get an idea if there was a great amount of deviation between one data set and the other. Maybe I started off like in a weird. There were a couple of those where I started off and I kind of wandered left and kind of back to center. Blake brought up a very good point. He noticed. I failed to notice this. The tape was not perfectly straight. It went down to about 75 feet at an angle, then kind of kicked back. It ended up being like a big, long triangle. Like 200 foot on one side. Well, actually not. Less than 200 feet on one side. And then 2 pieces that kind of added up to 200 feet. But it was such a small bend, I wasn't that worried about it. Over 200 feet. Not to mention all the other little inconsistencies in what I was doing with the bike. I mentioned on the way up the hill, butterfly effect. Anybody ever heard that phrase before? Help us. Yes, apparently it was a very terrible movie too, starring yes, very terrible. Yes, thank you. So, what is the butterfly effect? Besides the terrible movie starring Ashton Kutcher. Aaron, go.
What you alter in the past can affect the future.
Oh, good. Or even currently in the near past. So, I think that gets its phrase from the idea of a butterfly flaps its wings in Beijing. The atmospheric path that it puts in motion right then can affect the weather as far away as the United States. And you can often see this in rivers and things like that. You drop a pebble into a river, and it creates a ripple effect. And those ripples then create something else, which creates something else, creates something else. And things that seem completely unrelated at all actually end up influencing each other quite greatly. So I mentioned that riding back up the hill, mostly because there are all kinds of little variables that I wasn't controlling for. I hit a pothole on one of those trials at the very end. I didn't even see the first 3 times. I missed it the 4th time. But at the very end, there was a good size. I know it's hard to believe a pothole in a bend. Hard to believe that. But I mean, all kinds of things. So obviously my path wasn't perfect each time. But my assumption is it's perfect enough. Perfect-ish. So let's see what ish looks like. What we'll do is, let me just go across. I think I have space for 6 trials here, which I don't think we need. Let's delete that column. And let's go, my 25-foot group, just call out your times if you would.
3.32.
3.32.
3.35.
3.35.
3.47.
Oh, you're right. Sorry, guys. Hang on. Chalk that away. I'm putting them in the wrong place. Good call. Good call. 3.47. Thank you, sir. Keep going. Ian, thank you.
3.44. And then 3.35.
And 3.35. Not 23.35. 3.35. Okay. So that gives us an average of 3.386. That's the average time. How do you find an average? Add them all together, divide by 5. What does that number mean at the end of the day? 3.386 seconds. What does that mean? Like, everybody knows the formula, right? You add them up and divide by 5.
On average, that's the fastest speed you come up with.
Or the central C then, because some of them are faster, S. 332 is faster. 335 is a little faster. 344 slower. So what is the 3.386 telling me? Say that again.
Rate of speed, average rate of speed.
And what does that word average mean? I've never taught you this before. And it's one of these things I want to keep talking about now as we go through this course, because I want to plant the seed in your mind for when you go into your life and hear the word average uttered. Because how many have heard of an average? How many have sat through a guy like this side of the room? Yes. Okay. Don't write all this data down just now, friends. We're going to have a more concise data set soon. You guys are awesome. You're taking notes already. Good for you. We're going to have a much more concise data set to play with. We're not going to use all 5 from all 8 groups. That gets a little bit tedious. We're going to knock it down, maybe to averages. But again, what does the average mean? Please.
Would it be like the norm?
Oh, I love that, Alicia.
The norm of what it
I love what I just heard. The norm. Oh, the norm. Good. Very often, what the average is called an arithmetic mean, or the typical data point. Very nice, very nice. The typical data point. Now, I love that definition. It's one of the definitions my 243 often come up with in class when I pick their brains about this. And if you look at 3.386, were there any trials where I actually went 3.386 seconds? 3.32, 3.35, 3.47, 3.44, 3.35. I got two 3.35s, yay. But no 3. Tell me that. What's in your mind? I'm hearing words. Please, Brittany.
Isn't it giving your average if you had done it like 100 times, not just as
I like what I'm hearing over here. Assuming no goofy outlier data points, it's going to be roughly what I could expect on average, normally, over 100 or 1,000. I love the long term you're getting at here. It's very, very nice. But again, to super focus on just these 5, when you add everything up and then divide it by 5, what's that really doing? Good, I like that. Getting the central point of what? Of the data set? I like that, Randall. Aaron, go ahead.
Does this have anything to do with taking the squares?
Oh, it's actually the first step you would do in that idea, to find the average first and then find the deviation from that average, which is actually this, you can't see it because it's, let me widen this little guy right here. This little column deviation is actually the result of past that, taking the squares, averaging the squares, and then taking the square root to get back. There's very, very little deviation, 0.06, 600ths of a second. That makes me think that those times past that first marker were super consistent. Super consistent. So yes, it is part of that, the first part of that. Very nice connection, my friend. Let's come back to the average just in a second. Let's come back to that in a second. You see the next column over says medians? Medians 3.35. Anybody ever heard that phrase before? Have you have a median? Good. And there are many different kinds of medians. There's medians of the roads. I think I almost hit one today going down that hill. A median on a road is what? It's like a midline, right? They usually bend and plant things in them, which is amazing. Somehow they walk up to them. Yeah, so the median is actually like the geographic middle of a road. But some of you guys were using the word center with the average as well. And this is great, because they're both called measures of center. Yes, they are both called measures of center. But who remembers how to calculate a median? Remember how to calculate a median? If you've ever studied calculating a median, who remembers how to do it? A couple of hands, please, Taryn.
Don't you just put them from lowest to highest and pick the middle one?
If you took the 5 data points and put them low to high, it's the one in the middle. So you can actually see that median in the data set, yes? You have to arrange it in your mind, low to high, or high to low, doesn't matter, but the middle. So it looks like my low was the very first one, yes?
Yeah.
332, 335, 335, 344, 347. The third one listed was one of the 335s, I don't know which one it was. So the median is going to be usually one of the data points. Good. But again, back to the average. I haven't forgotten about that yet. When you add everything... Okay, let's stop right there. Let's forget this data for a second. Average number of children in the U.S. right now.
2.
Take guesses. 2.5, that was 1990. Remember from 1990, good for you. 2.5, I heard 1, I heard 1.7. Hang on, let's Google it. When was the last U.S. census? 2010? Was it 12? Excellent. Average number of children, U.S. family. I'm not going to worry about the definition of what a family is or the definition of what a child is. The World Fact Book, we're going to use that one. That's that's CIA. Afghanistan, American Samoa. This is good. Children born per woman. I don't want that. I want family. Here we go. We'll just use this one. This is fine. I don't care about the source at this point. I want a number. Answers.com. I love these. Be careful. And speaking of which, all I'm trying to do is get a number right now to talk about, to discuss right now. Hello, folks. You got to be careful, though. Always check the sourcing on these things. I found one of my favorite 244 questions is, I Googled, what is a p-value? Now, don't worry about this, because you'll learn it at 244 if you go down that road. If you Google what is a p-value, the first hit that comes up is a wrong answer. And that's the beauty and the downfall of the internet. Anybody can post anything anywhere. That's the beauty of it. Anybody can post anything anywhere. That's the problem with it, too. Anybody can put anything up, and if it gets enough hits, it rises to the top of Google's page rank. So I don't really care about this number being correct. I want to see the answer, though. According to the 2000 census, pi people, the average U.S. family size was pi, 3.14. I love that. That makes me happy. What does that mean? Ratio of what?
Average.
They can't use the word average, explain what the average is. That's circular reasoning.
I'm just saying, yeah, 0.14 kids.
Don't worry about that. Blake's asking a very good question. He's asking a very good question. His question is, what constitutes a family? I don't care about that right now. All I care about is that number and what it means. Assume that a family is well-defined. Assume that people is well-defined as well. It's pretty easier. Just assume everything's well-defined. Statistically speaking, I love your question, and it's very, very important. Very, very important, because it's very easy to misconstrue statistics by using poor definitions. What does it mean to have an average of 3.14 people?
It means it's 2 parents and 1 kid.
Maybe. Well, it's not 1 kid, though. It's 1.14 kids if you look at it that way.
Well, that's why I said it has to be the average.
Well, but it has to be the average because it's a decimal. It's a weird decimal, yes? Taryn, thank you, right? Taryn?
I was going to say it's like a balance of all the numbers bouncing off each other. I don't know how to...
No, this is perfect. Back there, one of you guys said the exact idea of where a center is. But so is the median in a different way. If you were to plot a graph of how many families have no kids, how many families have 1, how many families have 2, or how many families have 0 people, which is kind of silly. How many families have 1 person, 2 people, 3 people, 4 people? Clearly, you have to have a whole number of people per family. I mean, that makes sense, right? 1 person counts 1 time. If you were then to view that graph as a plate of cookies, where 1 cookie equals 1 family, you have a whole bunch with 1, a whole bunch with 2, a whole bunch with 3, a bunch with 4, a bunch with 5. I'm guessing as you get above 5, it's going to start balancing out a little bit more. Not many families with 7, 8, 9, 10, 16. There's some out there, I'm sure. What the average is it's where you'd have to put your finger to balance that plate of cookies. It is literally a balance point. That's perfectly said. Perfectly said. I wasn't going to go with that definition, but that's exactly what it is, Terry. How does that tie to the adding up and dividing by? How does it tie to the adding up and dividing by?
It's the same thing.
How is it the same thing?
Well, if you're taking all the families with all the data, they add all that together and divide by the amount of families they have, right?
That puts what in every family?
A child in every family.
Well, more general. If you take all the people in America and put them all together, and then divide by how many families there are, it's 3.14. Which means, remember that family that had 16 people in it? They don't have 16 people in it anymore. They now have 3.14. Remember the family that had 1 person in it? That family doesn't have 1 person anymore. That family has 3.14. This is the number that if every single family in America had the same number of people in it, it would be that number. So forget the fact that there are families with 16, forget that there is 1, forget that there is 2, forget that there is 8. If you had all the people in America divided by the number of families, it would break down to an even 3.14 people per family. Please, Aaron, go.
So is that eliminating the outliers then?
No, this I'm assuming takes into account the outliers as well. Because averages deal with outliers. They just add them in like everything else. I had my 243 class. You remember February 8th this year? Sure. Well, you do, because it was the one day this year that Bend got significant snow. Yes, the nods, yes. We got over 2 feet of snow that day. Saturday, February 8th. I got 25 inches at my house. I'm assuming depending on where you lived, you got more or less. I had my 243 kids. How does that change the average amount of snow on February 8th over time? And it can totally do it. It jumps. It depends on what years you're looking at. If you go from 1990 to 2014, the average was 0.2 inches. It's now 1.2 inches by including the 25 inches. Why? Because that's roughly 25 years. The 25 inches I got in my yard that day, I take that 25 inches and spread it equally to all the other years, thereby roughly adding 1 inch to each year. And that's what an average does. It takes the data and spreads it out equally across all the data points. Is this always a good idea? No! It's not always a good idea. It can be a bad idea. Imagine if wealth was distributed this way. Some argue that it is distributed this way. But that's the idea, right? The idea is it's not always a good idea, but it's used quite frequently, yes? So now you understand what it is. It's an equal share measure. It's a balance measure. It takes all the data sets, eradicates all variation, and says, you know what? If every family had 3.14 people in it, we'd have the same number of Americans that we do right now.
So we'd be living in China?
It looks like it-ish. Well, define a family.
Well,
Define a family. I've got friends in America, not even Asian families, that kept having girls until they had a boy. For some reason, they wanted to have a boy in their family. They got families of 7 and 8, and the youngest is a boy. That happens very often in China as well. The boy, for some reason, is more valued for whatever reason.
Well, because it carries on in the name.
Oh, it's one of those things.
Yeah.
Okay, I just think my mom should have stopped after 1, but whatever. So that's what an average is, friends. It's a balance point. Taryn, thank you for that. It's a balance point, but really, and tied into a balance point, as Aaron correctly surmised, is that it takes all the data, eradicates any deviations, and says this is the one number that would be the same across all the groups if you did this many times. And Brittany, whether it's 100 times, 1,000 times, 5 times. Thank you. That's what an average is. Everybody knows how to calculate it. But the reason, you see how the formula does it? It adds all the data together and then divides it by how many points. Doesn't that evenly make 5 data points that are the same? That's what division is, yes? It's repeated subtraction down to 0. Think about it. Why did you learn how to divide back in 3rd grade? Because you got time to subtracting. What is 22 divided by 2? 22 minus 2 is 20, minus 2 is 18, minus 2 is 16, minus 2 is 14, minus 2 is 12, minus 2 is 10, minus 2 is 8, minus 2 is 6, minus 2 is 4, minus 2 is 2, minus 2 is 0. 11! 22 divided by 2 is 11. Because you get tired of subtraction. That's why we invented division. But you got to remember what it's doing. It's taking even chunks. Each of those chunks are even to every other chunk. So when you see, goodbye pi family, when you see an average of 3.386 seconds, all that means simply is, if I had gone down the hill 3.386 seconds each time, I would have accumulated the same amount of time over the 5 trials as by doing it those 5 different ways. Is that fair? That's all an average is. More on that as we go through this class, because it's one of those things, even if you don't take any more classes after 105, math-wise or stat-wise, you will be inundated with averages the rest of your life. And you have to know. I love the question about outliers too, Aaron. In fact, one of you guys asked about outliers. I love that question because they can totally blow an average out of the water if you include them. Sometimes you want to, sometimes you don't. All right, let's get the rest of the times in and take our 5. Yes?
Yes.
Yes. Thank you, Francis. 50 feet. Oh, excellent. 50 feet. Where are my 50s? Shout them out. Shout them out.
4.94. 4.97. 4.83. 4.70. And 4.62.
Thank you so much. Beautiful. That averaged out to 4.8. A little more deviation on that one. A little more deviation. 0.15 seconds over there. Again, I'm not that concerned about 0.15 seconds. Any butterfly effect stuff that happened in the beginning would probably create a little more deviation, much like a hurricane. As they try to predict where the hurricane's going, it begins to get a wider path as it goes out. More susceptibility, more butterfly effect stuff going in there. 75 feet, shout them out!
672.
672.
606.
606.
622.
622.
618.
618.
606.
Thank you so much. 606. I'm a little concerned about that 72 there. We're going to have to do something about that. So we get rid of this curve too. I don't know what the hell that's going there. All right. Thank you. 100 feet, friends.
6.94.
94.
6.85.
85.
6.5.
52.
No, 5.3.
53.
Sorry.
That's, don't be sorry.
7.15.
15. 09. Okay. There we go. This, yeah, we'll come back to this. 125. Thank you for that. Perfect. 125s.
8.25.
25. 2. Crap. I have a hard time typing. 8.25. Go ahead.
7.94.
94.
8.1.
8 even. Holy crap.
7.88.
I'm taking credit for something I had no control over. Thank you very much. Beautiful. 150s.
8.95. 8.56. 8.91. 8.8.
Oh. 78. That was my bad, not you guys. You guys are perfect. Go ahead.
8.91. 8.85.
85.
And 8.81.
Thank you so much. All right. Over here to 175s.
We got 963, 959, 972,
Excellent.
978,
956.
Excellent. And at 200 feet.
10.03,
Oops. 10.03. Excellent.
9.90,
9.9.
9.9,
That's all good. All good.
10.25,
25.
and 10.22.
22. Is there one more or no?
Oh, number 2 is 10.91.
Not a problem. I'll just shove these guys up. 10.91.
Yes.
Excellent. Fantastic. You guys take 5. Let me clean the scatter plot up a little bit. We'll discuss the data. Come back, see if we need to throw any of it out. If we should keep it all, it's up to you guys. We'll make the decision together. But take 5. Let me get this stuff cleaned up.